Welcome to the Impulse and Thrust Fundamentals video. In this video, we're going to discuss impulse and thrust in the context of rockets. So, let's start. Thrust is the force generated by a rocket engine. Simple as that. Propellant is getting ejected at a high speed through the nozzle, and because of Newton's third law, if you push something, it will push back. So we are ejecting propellant. So a opposite momentum is coming towards the rocket. So it will go up, up. And what is impulse? That is thrust. Impulse is a product of thrust and time. And by intuition, you can think for that time, like thrust is just momentary. And if you combine many moments, it becomes impulse. Think of thrust as pushing force of a car engine, and impulse is how much total push it is generating during for a period of time. Like how much force that engine is generating during 10 seconds, during 20 seconds. That is impulse. Thrust is simple. I think it is of 1 second only. Okay. Now let's move to the other part. Formula of thrust. What is the formula of thrust? So here there are two things. Okay, there are two things. One is propellant is getting ejected out, and because of that, and Newton's third law of motion came into the picture, and mass flow rate into velocity of exhaust gases. One force is that. Another force is, what pressure difference also creates a force because the gases are ejecting out at some pressure. Okay, and there is some atmospheric pressure also if the rocket is still in our atmosphere, so that pressure difference into the area of nozzle also creates a force. We will see going forward in the video why it is important, why this force is so important. And also the formula of impulse is force into thrust into amount of time for which we are calculating the impulse, burn seconds. And it's also unit is Newton seconds. Okay. Now see rocket thrust changes with altitude. Rockets are designed like that. Like if rocket goes up, the thrust should increase. I was watching a SpaceX video last night, launch of Starship 7, I guess. So as the rocket is moving upward, the thrust of rocket was increasing and the speed is increasing at a very high speed. You know why? Because rockets are designed such that the thrust, the force will increase if it goes upward. You know why? Because see the thrust formula here. If this becomes zero, ambient pressure, the subtraction will not happen. So this quantity will automatically enlarge. This quantity will become big. Thrust will become big. So rocket's thrust increase with altitude because the pressure difference between nozzle exit and the surrounding environment becomes more favorable. This is why rockets are particularly effective in vacuum of space where they can operate at full efficiency and without any atmospheric resistance. So the atmosphere pressure is not there. So the rocket will increase that the rocket will accelerate. Simple. Atmospheric pressure is not there. That's why rockets are designed for vacuum. Because rockets are designed for space and space is vacuum. But that starship blew and the picture was so incredible. Blowing that starship. That's $100 million boom. Well, he has 400 billion, so what? So what? So what? So what? Rocket's nozzles are also designed. See, rockets nozzled. See, when you are making rocket, you have requirements. I want it to operate at 5,000 kilometers up altitude. I want to operate it at 10-kilometer altitude. I want it to operate at 20-kilometer altitude. So you define your requirements. So the nozzle area is like made according to the requirements. The goal is to match the exhaust pressure with the ambient pressure with the ambient pressure so that the rocket will peak its efficiency. Like if the nozzle exit pressure and if the what ambient pressure is what you say is matched na is equal, rocket will have peak efficiency because there will be no pressure losses. I guess that's why it is the reason. We will also discuss in the next video or next video. I know I don't know in which video. Like if the if this pressure difference is zero na P minus if this is equal, although it is looking like this term will become zero, so how it will increase the thrust? Somehow efficiency of rocket increases if we do this. Nozzle pressure is equal to ambient pressure at a specific altitude. We'll discuss in next videos. Now talk about a specific impulse. A specific impulse is measured in seconds. It is very confusing to for me if I studied this specific impulse first time. Specific impulse is like 299 seconds, 300 seconds. What the fuck is this? 299 seconds, 300 seconds, and we are measuring impulse in seconds. So, in specific impulses, how much, like for what amount of time, one mm, 1 liter of fuel can produce? Like how much thrust? How much for how what amount of time 1 liter of fuel can accelerate the rocket or can propel the rocket? You know, I have 1 liter of kerosene, and for what amount of time it will work or it will produce thrust. That's what impulse is. That's why it is 299 seconds, 300 seconds, 500 seconds. 500 seconds specific impulse means like for 500 seconds, 1 liter of fuel can survive. And let's come to the exhaust velocity. Exhaust velocity formula is this. Exhaust velocity formula is this. A specific impulse into gravitational constant g. No, it is g, not gravitational constant. G value 9.8. Why is it that? Why is that exhaust velocity is this? So if we go back to here, thrust is what? Thrust is m into v. Ignore this because I told you, no? Because rockets are designed such that it becomes zero. So put m dot v and m dot v there. M dot v and so that cancel. So v so upper part only remains ve and this goes here. So that's how you get this formula. Just put this there and you will get this formula. Well, what exhaust velocity is equal to specific impulse into gravitational constant. Okay, this is so exhaust velocity is important for calculation purposes. Yes. And solid rocket engines have exhaust velocity of 2000 to 3000 meters per second. Liquid have more, like up to 4500. Iron thrusters have much more. Iron thrusters, electric rockets have a velocities of 20,000 to 50,000 meters per second. There is a catch. Iron thrusters, I told in a previous video, it is made for deep space. It produces less thrust. Why? Why it produces less thrust? But for this large velocity, what is thrust? M into V. Velocity is very large in iron thrusters, very large, because they are being charged and propelled outwards. I'll come to that also. This mass flow rate is very less because the mass flow rate is very less. Na, we can like propel it or it can exit the exhaust gases or whatever it is at so high speeds. Still, the thrust is very low. Why? Because mass flow rate is very low. Although the velocity, exhaust velocities are very high, 20,000 meters per second, 50,000 meters per second, but thrust is very low compared to chemical rockets. That's why chemical rockets are popular. Elon Musk rocket is a chemical rocket, not a nuclear rocket. So, low mass flow rate is the reason iron thrusters cannot produce more thrust. That's and also the exhaust velocity is affected by nozzle design, chamber pressure, propellant, and many more things we'll discuss in the next videos. I hope the main point of the video is thrust. You got what is thrust, you got what is impulse, you got what is the formula of thrust, and this is some rocket diagram. What you and you also got what this rocket thrust increases with altitude, okay? And rocket nozzles are designed so that this term becomes zeros. This term, okay? Rockets are designed like that to peak the efficiency. And also you got formula. What is the specific impulse you got? What is exhaust velocity you got? This all you got. Goodbye. Thank you.